Yes. So today, I believe you'll remember the overall learning of statistics and probability. We're going to utilize this one way or the other. We're trying to build various models to basically implement machine learning. Decision tree is the basic element where or through which we build a model or we build those entities to enforce the learning into machine, into artificial intelligence, into the overall instruments we require to. Okay, so here let's start with decision tree. Again, this is a kind of revision for you, but please believe me, this is a kind of requirement. We are recursively improving our definition. We are recursively trying to understand the decision tree, how we make this decision tree, what we build as a kind of logical progression of event plus decisions to implement actual machine learning in a given scenario. Okay, so that's what the today's most important learning as far as how to implement decision tree or how to basically have the machine starts learning something. Okay, so let's start with this. Decision tree is the most powerful and popular tool for classification and predictions. As we go on improving on various tree branches, progressions, we try to extrapolate these decisions. We try to go ahead even our after our boundaries and try to basically plot down certain probabilities to make sure how this will go on if it's gone on ahead and ahead. In decision tree, earlier definition we said we'll stop till the actual thought process stop or till we have the end results. But here, when we try to extrapolate those end results and try to gather how much end results we gather, how much end results we do collect, we try to go beyond them and start understanding how we can have these models implemented in a given models. Okay, so let's try to understand. A decision tree is the most powerful and popular tool for classification and prediction. A decision tree is a flowchart like tree structure where each internal node denotes a taste, denotes a path, denotes an alternative, an attribute. Each branch represents an outcome of a test, or each leaf node or a terminal node holds a class label. Now here what we are trying to do, we are trying to understand how to utilize this decision tree in a programmatical model, or how do we implement the decisions which we have taken in a decision tree of which nodes to be taken and implement it in a programmatical model with some either if else or some decision making techniques within our program. Okay, does that make sense?
Yes.
So slowly, steadily, what we are trying to do, we are trying to reach to a level where the program should be able to decide on its own with a given predefined variable, attributes, factors, and then we'll move ahead with the next branch, next tree, and so on and so forth. A tree can be learned by splitting the source set into subset based on an attribute value test. We'll learn how, but let's try to understand, let's try to think it through. A tree can be learned, can be taught. Learned in the sense if it's learning by itself. Most of the scenario, it learns by itself. That's why we say learn rather than taught. A tree can be learned by splitting source set into subset based on an attribute value test. So if the attribute value changes, the branch changes, the event changes, the branch changes, the occurrence or contents of a variable changes, the branch changes, the decision changes. This process is repeated on each derived subset in a recursive manner called recursive partitioning. We had a look at these things in our probabilitical understanding. The recursion is completed when the subset at a node all has the same value of a target variable, or when splitting no longer adds a value to the prediction. What we said, when we understand this is the final result, this is the final outcome what we are looking for, that time we stops. Now what we are trying to do, how we reach there, capture those decisions in a programmatical manner, in a manner where we can implement it for a given set of progressions. The construction of a decision tree classifier does not require any domain knowledge or a parameter setting, and therefore is appropriate for exploratory knowledge of discovery. Now, what does this mean? The construction of a tree does not require domain knowledge. I don't have to know the which medicine is to be given to a patient. Only I need to make sure the patient goes to a doctor. Means I don't have to really understand how the medicine affects the body. What I believe is basically this is how we get the medicine, and then this is how I get myself repaired, corrected, in the right way. And that's how we start learning. So the path is more important than the result. Well, the result is an end point, but we can still keep walking till we incur the result, till we capture the result. Decision tree can handle high dimension data. As we know, we are into programmatical world where we can basically tap each and every probability, each and every alternative given to us, and try to reach the end result, because the possibilities can be easily calculated if you have the finite model. Even if you have an infinite model, I still can go recursively partitioning and try to attain a value which is for me is a finite for a given subset. In general, the decision tree classifier has a good accuracy, definitely, because we are playing within the bandwidth of our statistics and with a given probability. So we have the width of a path and we have a result in mind or a target in mind. And that's why this decision tree has a fairly good accuracy. Well, sometimes it can go away. And that's why we say, okay, now the target is really out of bounds or out of the data width. So we need to either change the data path, change the alternative, or try to think it more nearer results, more achievable results. The decision tree introduction is a typical inductive approach to learn knowledge on classification. Now, this is a really important part. Decision tree induction is a typical inductive approach to learn knowledge on classification. So what we are doing at the end of the day, we are just trying to find the alternative paths available to me. And how do we find? We find it through entropy and gain. So we try to address more and more gain and less entropy on the way. And we do it with recursively partitioning. Does that make sense? Is it in line with the thought process you thought of in terms of machine learning?
Yeah.
Yes.
No? Okay. Yeah, please tell me what contradicts. Who said no? I haven't these things. Balaji, yeah. Have you said
yes. I said yes, so I don't know.
I said yes also.
Okay, you said this. Okay, sorry. So we are on the right path, right? If there are a contradiction in your thought process, please do let me know. We might go over this thing again, because this is why we learn decision tree. And decision tree, as I told you, is a basic evolutionary alternatives and event pair we keep tracking to reach our final goal, what's to implement programmatically in a given scenario. Okay, now here we are talking superficially, but in a few slides, we'll basically try to build these things on a practical Python level. So let me play a good video for you where we will try to understand how do we do it with decision tree. How do we start thinking in terms of progressively achieving more gain? A data set to match the required result. We try selecting on different parameters or different events progressively, and then decide how we can reach the perfect expected results. So what we are trying to do, we are trying to basically match the pattern along the way, or match the pattern recursively, progressively. That's the most basic thing we do in terms of decision tree implementation in a given program for attaining some gain. Now these gains can be at a different level, and we achieve it by step. That's the most important thing we need to learn. And you need to explain this to the interviewer. This is again normally third most probable asked questions in a data science interview. Tell me about decision tree and the types. So even we need to practice on these things. What are the types of decision tree and how do we achieve or how do we implement this decision tree for a given type of machine learning. So let's try to dwell on more on machine learning now. So machine learning as a topic, right? So what we are trying to do, machine learning is a study of computer algorithms, patterns, how do you implement the choosing mechanism or the, progressive mechanism for a partitioned recursively progressive decision tree. So again, machine learning is a study of computer algorithm that can improve automatically through experience and by the use of data. Now, what do you mean by through experience? We implement better decision tree as we go on moving and understanding the alternative paths and probabilities. And with the use of attributes or different status of attributes, different contents of attributes, we try to choose different branch of decision tree. And that's you progressively we implement via some computer algorithm or via pattern matching, via some selective choices within these status of variable. So that's how machine learning is a study of computer algorithms that can improve automatically through the experience and by use of data. Does that make sense? Anybody have any confusion?
I'm good.
You're good, right? Okay, great. I hope the others as well. Otherwise, please speak out. These are the one of the few things which we need to really practices either way for the interviewing thing. Okay, it is seen as a part of artificial intelligence. As we know, ML machine learning is a part of AI. Machine learning algorithms build a model based sample data, right? As that I have said, the Google employee will have more than 100. But that's again, that was the assumption for a given model data. And then we start on achieving that data. So once we have that data, we'll categorize those data sets or those data sets content into a particular another group of these things. So that's the result what we've achieved. Machine learning algorithms build a model based on a sample data known as training data. Now, training data is the end result what we are trying for, or we are marking our decision tree for the trained data or for the data which we know should be the end result. In order to make prediction or decision without being explicitly programmed to do so. What do you mean by explicitly programmed? We try to choose between different data sets. We try to filter it out in a progressive recursive partitioning model. And that's what we try to evolutionary predict with a what you can say exponentials reaching to that given result data. Machine learning algorithms are used in a wide variety of applications such as medicine, email filtering, blah 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 blah, speech recognition, computer vision, driverless car, and so on and so forth, where it is difficult to unfeasible to develop conventional algorithm to perform the needed task. Now let's think here where we implement machine learning and how to implement it with a kind of precisions or with the kind of a finite predictions. Let's start with a simple example of choosing apple over banana. Now, as you know, apple is more spherical, banana is more, on a oval shape or elongated shape. So, trying to capture or trying to distinguish these two pictures is pretty easy. Because if you know the pattern wise, the patterns are pretty different. But when you say apple versus orange, now both are spherical in nature. Then we have another predictions or another what you can say algorithms to apply to the color, the refractiveness of it, and so on and so forth, or the shape at a particular juncture of a given image, or a color progression of at a particular juncture with a given end of the image. If you know apple get lighter on the end of the where the apple is attached to the tree, but orange is pretty much uniform in color throughout its spherical existence. And that's how this algorithm or these patterns we are trying to match on a decision tree. So progressively, what we do, we try to teach machine try to teach the, classify image on a in a general progression case where we try to understand how to differentiate between apple and banana or apple and orange, and slowly, progressively, we try to achieve the machine can predict apples and oranges for us. Can it do for 100 and accurately as humans? Well, in most of the scenario, yes, but there could be some exceptions as well. Now we understand there are some gain, there are some entropy. Now these terms do matter because we need to ignore entropy. We need to attain more gain in a step-by-step or a progressive manner. So whenever we get more of an entropy, more than 50%, we will try to what you can say, initialize the thought process, reinitialize the algorithm to make sure we reach at least more than 60% accuracy in a given model. Otherwise, we'll change the model or we'll improve the model. And that's how the recursive partitioning do help me to reach to my attainable goal or try to reach more accuracy than what we have predicted earlier. And that's why machine learning is a evolutionary learning for a given machine. So the more you practice, the more you understand, the more you can basically attain more gains or attain more accuracy in a step-by-step way. A subset of machine learning is closely related to computational data statistics. Why do we say that? Because as we just discussed, whenever you try to understand apple versus banana, you're trying to apply statistics and probability in terms of matching those patterns in a given image. You'll understand when we do hands-on practice, but I'm just trying to basically give you the idea, how do we implement machine learning in a given device? A subset of machine learning is closely related to computational statistics, which focuses on making prediction using computers. But not all machine learning is a statistical learning. Yes, sometimes we normally go by understanding different algorithms which are not related to statistics or probability, but we try to invent some out-of-box thinking to build some accuracy within our algorithm or try to remove entropy within our algorithms what we build to understand or to learn. A subset of machine learning is closely related to computer statistics, which focus on making prediction using computers, but not all machine learning is a statistical learning. The study of mathematical optimization delivers methods, theory and applications, domains to the field of machine learning. So we try to understand, try to build this predictiveness with the statistical model or a probability models. But in some scenario, we might choose some, exceptional scenario, we can say, we might choose some out of the box thinking of understanding, let's say apple versus orange. Okay, even for that matters, apple versus banana, whenever we try to understand the basic difference, elongated or spherical type of fruit, here we are trying to understand or try to analyze the image based on the pure geometrical need rather than statistical need, right? So on and so forth. So sometimes or predominantly you use statistical or probability model most of the time, but sometimes we might have to choose another alternative to make it more accurate. Data mining is related to the field of study, as we know. This is what we call data mining, right? Capture a photo, try to let the machine decide if it's apple or banana, apple or orange or so on and so forth. Okay, and this way what we do, we are trying to understand how the progression of our decision tree is being implemented in a given program. So data mining is related to some implementation of machine learning, use data and neural networks in a way that mimics the working of a biological brain. So how do we learn banana is elongated, apple is spherical? Because we have experienced it. We as a human know that difference. So that's why we have implemented these models in a given program so that even machine can understand the difference or machine can go on predicting in a particularly defined decision tree. It in its application across the business problems, machine learning is also referred as a predictive analysis. Now we'll try to understand how these analytics or how this progressive decision tree implementation does make me build some branches into machine learning. We'll learn in a few slides, but first that way, let's try to understand the leaders within machine learning space even now with the help of others, of course. IBM International Business Machine is one of the most important leader in machine learning for a given times. And this was there for at least a couple of years now. So that's why we can say clearly how AI or how ML is being progressed by these leaders in a particular way. Okay, even IBM contributes quite a good amount of its programs or machine learning patterns or algorithms, and they share with you. So that's why we should always have a look at IBM's website whenever we try to learn certain new things about ML. Okay, now let me start with saying machine learning is a kind of evolutionary bias, as we discussed. So how these industry leaders are implementing machine learning as of now, as of 2020, in a given applicable or mathematical model. Machine learning is a branch of AI and computer science which focus on use of data and algorithms to imitate the way that human learns, gradually improving accuracy. So how do we attain accuracy? We try to match our patterns, our decision tree based on human learning. Okay. Now let's try to understand a bit of history so that we are more in alignment with the actual scientific approach to it. Okay. And we'll try to reduce the other approaches from our thought process. IBM Arthur Samuel credited for containing the term machine learning with its research in 1962. So this was a kind of first data scientist we normally refer to. Even within computer programming, if you get a question who is the forefather of ML, then this Arthur Samuel is. In 1962, he basically registered this term machine learning, and then he started working on that. He lost to the computer compared to what can be done today. Speed almost seems travel, but it's considered as a major milestone within the field of AI. Over the next couple of decades, I mean decades, yes, decades, not years. Over the next couple of decades, the technological development around the storage and processing power enabled us to innovate some products as we know or as we have today, such as Netflix recommendation engine or self-driving cars. Now, these are one of the most front runner of the ML, paradigm in terms of self-decisive programs. Netflix, we have seen the case study. Self-driving car, I'll explain in few slides, mostly next session. And how do we implement ML? But I believe you got a hint, got an idea how we progress on ML, how we progress on building this program to let us know more of a predictive result or to build some predictive business decisions for us, for a data scientist. Machine learning is an important component of a growing field of data science. Through the use of statistical methods, algorithms are trained to make predictions. Now, prediction means a business inferential decisions which can come out of a program. That's a kind of a proactive predicted solution for a given data scientist solution, right? Through the use of statistical method, algorithms are trained to make predictions, uncovering the key insights of a data mining project. Now, as we know, data mining is there for last 70, 80 years. Now, what we are trying to do, we are trying to build some predictive business-like decisions from these data mining solutions. These insights subsequently drive decision making and applications and business, ideally impacting the key growth metrics. So why business is using data science? To implement or to align its growth in a market or to align its overall, brand making, profitability making, the growth in a particular region and so on and so forth within their business applications models. Now, a big data continues to expand and grow. The market demand for data scientists will increase, requiring them to assist in identification of most relevant business questions and subsequently the data to answer them. Now, here the most funniest thing what IBM says is basically we are generating the requirement and we are giving the solutions. So typically data scientists don't get the requirement outside. They generate the requirements by themselves depending upon the thought process of a business. Let's say whenever Netflix, CEO, CTO says, I want to develop a new sitcom for Midwest region. No, as we all know, Midwest is a Bible Belt or whatnot you can mean by that. So what we have to build, we need to build some religious sitcoms, or we need to build some mythological sitcom. We need to build some sitcoms which reflects the society, culture, and so on. Now, we have learned these things? We have learned these things from the data available to us. And from that, we generate these requirements. Okay, so next sitcom will be of so and so type. Now we also provide the business with how to, which subject will be more relevant in a given demand. This is we have understood from the exploiting the curve or extending the curve or extending the distance tree to a level where we get a result of most probabilical demanded show or demanded sitcom for a given region. And this is how we build the requirement and we build the solution. Does that make a sense to you, what I'm trying to say?
Yeah.
And this is what available on IBM website. Please do have a look at ibm.com/AI and you'll get all these, I've copied these text from there basically. A big data continues to expand and grow. The market demand for data scientists will increase, requiring them to assist the identification of most relevant business questions. Again, these business questions are the requirement and subsequently a data to answer them or build a data solutions as an answer for these requirements. That's why the data scientists, they are analyzing the data continuously, they are researching the data continuously, and they are building the solution for the given problem. That's why data scientists are continuously required, because we mine the data, we analyze the data as it grows, and we build around that data. So again, we build these decision tree continuously, recursively, in a step-by-step manner or an evolutionary model. And that's what the IBM taught us over the past few decades, where we'll try to understand. Even we couldn't acquire driverless car. Okay, who can basically guide me on driverless car or how self-driving car and use of machine learning? Who could want to extrapolate their thought process? Because we have, I think, understood the decision tree now fairly well. We have understood how to implement this decision tree in a given problem, right? So who can tell me how self-driving car can use ML in a day-to-day life? You know the concept of self-learning car, right? Who don't know self-learning cars concept as of now? Anybody?
I have a basic understanding of it,
Okay,
but I guess
that's fair.
I'm guessing self-driving cars are using like AI and stuff by mapping out the road. But like say you're taking the same route to work every day, and the car is mapping out the same route. So when you say you have a Tesla or something and you put it on autopilot, then the car will automatically know which route to take, and you don't have to basically drive the car.
Right. You have told me the requirement which is auxiliary in nature. I want to understand the main requirement, how to remove obstacle or how to steer away from the obstacle. That's the main AI part of it, driving early. Don't think it as a wrong or right.
Oh,
Please.
okay. So like by using the cameras on the exterior of the vehicle, I guess.
Requirement, right? Now, how do you, as a data scientist, will implement decision tree for those type of challenges?
So I guess you would have to see what the camera is looking at. So if it's like a cone, or if it's a human, or if it's an animal, then the AI would have to differentiate what the obstacle is in front of you.
Perfect. Perfect. One way. Now, just to add to that, as we are thinking on a self-driving car, and believe me, this is a need. Whenever an interviewer asks you, how do you implement AI in a particular example? You need to start thinking, and believe me, there are quite a few new number of challenges. I have taken a simple, thought process of self-driving car, which we know as a solution, how they have generated. But an interviewer, a brilliant interviewer normally give you an example of a difficult topic, and we'll discuss on that subsequently. But right now, let's try to understand how do you build a decision tree for a self-driving car. Let's spend 2-3 minutes. I don't want to spend too much time on this, but this is again how we progressively partition the decision tree by ourselves as a data scientist. So we need to start thinking in terms of scientific manner. Now, a cameras alone couldn't suffice the need, and this is what we have found over the years. If you study those papers, if you study those various case studies available on IBM, IEEE, and even on Boston Dynamics, because Boston Dynamics have, as I told you, 4 commercially available robots right now who had these machine the algorithms implemented them to avoid obstacles. Okay. Now let's come back to the decision tree or implementation of a decision tree. Camera couldn't suffice the need to steer away from obstacles. You might have couple of cameras. Well, a typical self-driving car has around 12 cameras, means 3 on each side, and that's a normal understanding to make sure if there's a light. This is because just to understand the obstacles shape and size and the movement, and on top of that, even the movements of the given object are not correctly mapped or calculated by the cameras alone. So we use something called lidar, LIDER. Now these are a kind of laser guns, to be precise. If you want, I can talk more on lidar also. We did quite a few proof of concept for technology business incubation in India, where we try to implement how lidar reads, how we can clearly understand the obstacles movements than obstacles identifications. Now, as we told, in a driving car, when you go on a road progressively, we need to categorize if the obstacle is coming your way, because these are all moving real-time objects. These are not just the image, the way camera captures you. Even if you have a moving cameras, still the movement captured by moving cameras are not fairly accurate in terms of measuring the direction and progression. Believe me, you might learn these thing and you'll find that. Now these lidars are basically multiple laser guns who try to calculate the distance between you as in prime and object as in second. And there we try to extrapolate the collision course. If you have ever seen that, Star Trek movie, they have really shown this thing as in graphs in quite a few of their, plots, plans, or scenes. How basically the collision course is plotted for a given object. Okay, now this was a bit of old concept, so that's why those movies are really using it well. So these collision course type of predictions, or what you can say, progressive recursive distant tree, what we implement in a given scenario are from lidars. And above lidars, we also use ultrasonic guns just to make sure whatever data collected by lidars are are validated at a certain level by these sonic guns. We call them sonic guns, or you can ultrasonic sensors, or whatever you want to call them. Depend on all these 3 parameters. We have video cameras, we have lidars, and we have these sonic guns. Then we decide where the obstacle is. Is it moving? Is it stationary? Because we are moving, right? As in prime object, we are moving on a road. And then we're trying to gauge the referensive progression of others. And that's how the decision tree gets progressed on a multiple level. And that's how we try to understand if anybody is going to hit us on head on. And that's why the collision course is really one important, you can say, branch of a decision tree for a self-driving cars. So whenever somebody asks you about self-driving cars, please do talk about this collision course and why we need all these, various cameras in the video camera or streaming cameras, lidars, LIDAR lidar, sonic cams or sonic guns or ultrasound sensors to understand the progression of the obstacles if he she is moving, and if there's a collision course, how to avoid those collision course. And that's what the most crucial part of the AI in self-driving cars. Of course, the complete case studies of ML. But overall, we have to categorize all these different decision trees. Now, I'm saying different decision trees and the branches because if you look at these three different data stream inputs, on one end we have images to categorize to. One end I have laser guns data to analyze to. Other I have another ultrasonic or sonic guns or sonic sensors data to analyze to make sure whatever I am getting is validated as incorrect, and then I can predict the decision based on those things. Does that make sense to you, or I'm just talking really vague English?
I'm good.
Okay, so you know what I'm talking, right? Means you can relate to the actual thought process. This is really important to understand,
Yeah.
and you should be able to explain by yourself. That's the need of the art. Okay, so please do make some answers or try to answer these questions. Like, tell me something about ML in self-driving cars, ML in Netflix. Netflix, we had a really good videos. We had seen a couple of videos, so I believe you got an idea how to predict a best marketing sitcom for a given region, and that's how they work normally. Well, they have quite evolved model for themselves as of today, and they keep evolving them. So there are multiple algorithms, multiple alternatives that are play for a process. But still, self-driving car is more of a techie example. Netflix is more of a data playing type of example. Of course, as a data scientist, we work on both. And just to give you a next step of self-driving car is basically the mass Land Rover. Why is difficult? Think it through, and we'll discuss in our next session. Okay, I'm not stopping right now. I'm just giving you a homework. So think it through. How mass Land Rovers driving is different from self-driving cars we have in our day-to-day life. Okay, and we'll debate on that. How the ML or the decision tree analysis is different there. Okay, this is just a homework or a food for your thought. Machine learning is an important component of a growing field of data science, though the use of statistical methods, algorithms are trained to make predictions, uncovering the key insight within the data mining projects. Now, what we are trying to do here, we have certain learnings, we have certain already made predictions and a history of understanding, and we try to match our progression with those our history or the events which happened in the past, and how do we relate to them, and how do we learn from them, and progressively, recursively partitioning the decision tree for the decisions which comes next in your progression of algorithms. These insights subsequently drive decision making within the applications and business, ideally impacting the key growth matrix. Now, when you say matrices, here we are talking about all these predictions or all the history of data we collected and we are learned from them. So this is, you can say, a pair of event and a decision. So for such event, you need to take such decision, and so on and so forth. So we build these matrices to guide the machine rather than calculating each and every time. You can refer to these matrices and basically take the decision based on event decision type of knowledge. It's not as simple as we talk, but yes, at the end of the day, it will be as simple as it talks, and we are still reaching there. And we'll categorize how this ML progression do happens and how do we basically categorize this decision tree or the predictions which we are trying to achieve. A big data continues to expand and grow. We talked about that, right? Okay, yeah. So this is how we are improving day by day in terms of machine learning. Okay, let me take a step further and try to categorize this machine learning. Now, these three terms are normally talked over and over again: AI, machine learning, and deep learning. Now, artificial intelligence is what we call the intelligence artificially induced into a system. So when I tell Alexa, Alexa, could you please, play some song for me? It's AI, but still, it's now what can be achieved earlier. So we called it, recursively command model. So what happens on the ground? Okay, can anybody tell me how does Alexa functions? When I'll tell Alexa, Alexa, play me some song. So how does Alexa works? Can anybody ever thought on that? Can anybody describe those things? Now here, the most important part as a data scientist, we're trying to understand how the machine learning is implemented in that dabba, in that box, in that dumb terminal who only know on and off. Okay, please try to explain.
When we say Alexa, then the program starts out and it tries to analyze the next sentence, and then it'll see, then it'll take the sentence, parse it, and then
Madam, 1 minute. Don't say is analyze a sentence, is analyze the audio file. Let's try to be more techy, right? Because we are at a level where we try to analyze the exact technical terminology. So try to use more technical terms. So Alexa listens to your sound command and it analyzes the sound file, right?
okay.
It can be wave, this thing, that thing, and converts that sound file to textual, what you can say, recorded terms, right? Yeah, please go. Sorry. I'm not discussing you, madam. I'm trying to.
No, I didn't say anything. I was just listening to you.
Don't take it otherwise. Huh? We are discussing here as your friends, as an one-on-one. So
Sure.
and we are preparing for interview also step by step, and that's my intention here. Okay. Again, there's no right or wrong here. We are evolutionary learning. Please go ahead, ma'am.
Yeah. So first it analyzes the audio, and then it'll take the sentence, and then probably like how we type in Google, that's how it goes there, and then tries to see what was the instruction given to it. And then I was just thinking it'll take the audio file, then convert it into the text, and like how we do a Google search, it does the same thing with the audio instruction, and then finds the wherever the solution is and gets it to us.
Perfect. Perfect. This is really good, but I would really, have you go through the Alexa's, the documents available on the net? Means even Amazon have contributed to the open source libraries, how Alexa works and all those things. Even there are programs available for converting an audio into a command. And these are as small as like you can get it work with Arindo or, Raspberry Pi as well. Means there are quite a few, audio instructors or audio listeners, as you normally say, for a given set of Internet of Things devices or IoT devices, and you can learn from them also. So for for us as a data scientist, here what I'm trying to understand, it's a basic instructional model created out of audio file and basically programmed to give output based on audio instructions, and that's what the Alexa do as explained. Okay, now let's go deep in terms of machine learning. Let's say if I ask Alexa, what was the, what will be the temperature of 3 days from now, or predict me the season day after tomorrow. I want to go out or something. So how it will do? It'll basically try to understand or try to go to a site where it normally get those weather predictions. Bluntly, that's what's happening right now. it has some data feed connected to its server. So it checks with, okay, tell me how will be the weather on day after tomorrow. So that audio file will be played for you. Okay, day after tomorrow, this date, that day, and in the morning we are expecting this much Fahrenheit, in the afternoon this much Fahrenheit, rain, snow, whatnot and whatnot, right? So that's the kind of recorded thing. If I take a step further and if I ask him how much snow is expected or what's the probability of snowing on that day, and if the data feed don't have, Alexa will come back to you. I don't, I don't have an answer for that. Now, this is a kind of predicted machine learning, or what you can say, predicted.
Hello, I
Yeah.
think we lost.
Hello. Yeah. I think we
Lost
lost
the audio.
him, right?
I think we lost the audio, his audio.
Yeah, that's true.
Okay, pardon me. Where do you lost me? Sorry, I think I lost my connection or something like that. Sorry.
Yeah.
Where do you
Yeah. I think you were trying to learn, trying to explain artificial intelligence, I believe. So that's where I think it went on mute. Yeah.
So in machine learning, whenever we try to achieve something, extraordinary, there are some mechanism by which we normally give them a predicted result. Like Alexa will answer to you, sorry, pardon me, I don't know the answer for this question. Let me come back to you or something like that. And it will basically report the exception to the developer body, to the support body within the Alexa gamut, because it's connected, because they have the data feeds going on with the support stuff as well. So all these exceptional things are collected at Alexa Development Center, and they keep building these decision tree or pardon me, extending this decision tree in a step-by-step or recursive manner. Now, deep learning. AI is simple superset, machine learning is a subset, and deep learning is another subset. Now, why we segregate these things? We segregate deep learning because here we are trying to go to multi-level deep. Believe me, these levels on in terms of number of exceptions, number of result I am building in terms of these exceptions, and how deep I can go. In terms of Alexa, we can clearly say it's a deep learning mechanism because the exceptions are being solved, might be in a day, might be in a week, or might be in a month, but at some time you get those answers for whatever the database is not yet built at that time. And that's why Alexa is a real successful model, or Google Home is a successful model. If you look at other counterparts, smaller counterparts, cheaper counterparts, they are still struggling with these predictive models. Well, they have implemented in a way learning from Alexa and Google Home, but still they haven't reached that level. The database of or the what you can say extended decision tree with Alexa or Google Home is really extensive in a nature, so that we are reducing the probabilities of unanswered question day by day, months by months, week by weeks. Okay, and these comparisons do make us more intrigued in terms of how we can improve AI. Now, AI is not just the deep learning or machine learning. AI is a more bigger fish or more bigger superset, where we normally include robotics. We normally include robotics in the sense repetitive machinery. Let's say in Tesla, all these cars get painted by robots. It's a truth basically. I've seen the Tesla's this thing. All the cars which are built at Tesla are normally painted by robots, just to make sure. Why they do this thing? Because of the perfections. because of the exact tint they need for certain curves and so on and so forth. So AI is basically whatever we have actually learned in the past, as in machine learning, we implement that to a perfection. And that's why those already what you can say exhausted decision tree. Why I say exhausted, or you can say completed. Okay, completed decision tree are perfectly implemented in a machine world. What does that mean? That means that certain use cases have been achieved its perfection. Now there's nothing to be achieved after that. So those machines are already pre-programmed for certain combination and permutation and combinations, and they keep executing the best, precisive models in their decision trees. It's not evolutionary model. It was a finite models, and we have already achieved that model. Are you getting me what I'm trying to explain here? Any confusion on already exhausted decision tree? Have you understood what you mean by exhausted decision tree?
Yes.
Yes.
Okay. This is really important for our thought process as a data scientist. So when we talk about exhausted decision tree, you could remember example like car paint job in Tesla, and there are quite a few car manufacturers using these robots because Tesla have given that royalty and so on and so forth. Even Ford had one built for them, which is separate from Tesla. But of course, Ford uses around, I think, 16 different robots. Tesla uses some 6-9 robots. These case studies are available on IEEE site. They called car painting robots case studies. And you can Google it. You'll have quite a few from Fords and Tesla as well. Have a look at them. Now, these are the decision trees which are already finite. There are certain permutation combination reach their numbers, and you can't go beyond that. Well, you can have a small car, bigger car, 4-door car, 2-door car, and so on and so forth. But we have already exhausted those alternative and results set. We have achieved this learning. So these type of finite decision tree implemented in a given Internet of Things or robotics are normally in use in the industries. And these examples are really great, or really tell us like we can achieve perfection up to a great extent. Now, how do we decide these machine learning, or how do we differentiate these machine learnings within the set of AI, ML, or deep learning? Okay, we'll see that on those in couple of next slides. Okay, so let me take you further. Any questions on these differences of AI, ML, deep learning?
No.
Okay, great. Thank you. If you have any questions, we can basically discuss on WhatsApp as well. No problem there. Or we can discuss in our next term as well. Now let's try to understand how do we build these models? How do we basically try to achieve these models in terms of decision tree, and what are the finite, infinite, or continuously learning, and how do we share these things, and how do we categorize these machine learnings in a way where we can apply in a real life scenario, right? I have a good video for that. Let me share that video for you, and we'll understand how machine learning models are being categorized. We basically will try to understand the machine learning, the different models, understanding of deep learning and machine learning, their differences, neural networks, then how machine learning is basically implemented practically into programming, and then we are going on dwelling in supervised learning, unsupervised learning, reinforcement learning, and so on and so forth. Okay, so now we are getting into more and more actual programming, actual building of solution. So please don't miss any class. Let me know if you have problems. We might skip a class or two. Okay. Additionally, I have my LLM exam on 1st, 2nd, 3rd, and 4th. So we might skip 2 classes. That's in the next next week. In the next weekend or something around that. Okay, not this weekend, next weekend. And I'll guide you on that. Don't worry on that part. Okay. So if you have any challenges, please do homework. Please try to watch this video a couple of times and understand how we actually categorize machine learning based on the decision tree, the models, and the learning itself, right? And then we'll start with the going into actual categorizing these machine learning and how we build this model programmatically in our next session. Okay. Any question for me at this moment?
No, we are good, sir. Yeah.
You're good. Please have a look at these videos, and we'll basically debate more. Okay. Chalo. Thanks a lot for your time. Have a good night. Bye bye. Take care.
Good night.
Thank you. Thank you.